Welcome everyone to the Royal Astronomical Society. My name is Sian Prosser and I run the library and archive. And it's my great honour to introduce our speaker, Anna Von Mertens. And she'll be talking about Henrietta Swan Leavitt today. And Anna is a visual artist and author whose work has been displayed across the United States and internationally, is uniquely qualified to talk across the disciplines of art and science, to talk to us today about this amazing astronomer, about her creative methodologies, about her discoveries. Von Mertens is actually primarily a textile artist who uses traditional quilting methods to create conceptual art. And she's used her artwork as a lens to see science and history. Her new book, Attention is Discovery, The Life and Legacy of Astronomer Henrietta Leavitt, grew out of the 2019 exhibition Measure, which was commissioned by the Harvard Radcliffe Institute. Von Mertens explored the life and work of Henrietta Leavitt. She did this by delving into the glass plate astronomical photograph collections at Harvard and went on to receive an Alfred P. Sloan Foundation in the public understanding of science and technology. She was benefiting from this grant because her work, she told me, couldn't stop with the Measure exhibition. She had to continue delving into the life and work of Henrietta Swan Leavitt. So she developed her research into the book that I mentioned. She's also received a Smithsonian Artist Research Fellowship at the Smithsonian Astrophysical Observatory in Cambridge, Massachusetts, where she's been studying dark matter. And she's received a US Artist Fellowship in Visual Arts. So I'm very honored to hand over to Anna.
Thank you, Sian, for that introduction. Thank you for having me. I was just up in the library and thinking what an honor and a delight it is to be able to talk about Henrietta Leavitt here under this roof in this institution. It is incredibly meaningful. So as Sian said, I'm primarily a visual artist. And let me cue up the first slide. And this happened last time where the slides did not advance. And I needed Lucinda's magic touch, but you moving helped. It made it happen. Okay. So as Sian mentioned, I am primarily a visual artist, and I'm interested in systems of mapping. I think one thing that both art and science do well is sort of pull patterns forward as a way to try to understand this world that we inhabit. And so this particular body of work that are hand-stitched quilts, the particular mapping system or pattern shown here is the ways that galaxies organize around extremely massive gravitational basins of attraction. And my particular interest in sort of where we are is very much an existential one, helping us to figure out who we are. And for specific reference, the Milky Way galaxy is at the tip of one of those branches there, headed towards this basin of attraction, so-called basin of attraction. These patterns, this underlying structure is the origin of that story of where that comes from, this knowing the structure to our universe. That narrative often begins with this glass plate. It was taken in 1923 at Mount Wilson Observatory by Edwin Hubble. And it sort of marks the beginning of modern cosmology. Edwin Hubble was tracking new stars that flared into view, that registered on his glass plate in the Andromeda Nebula, as it was called at the time. But when he compared it to the plate taken the previous evening, he noticed that one of those stars changed in its brightness. It was not the characteristic of a nova, but that of a variable star. So he returned to that original plate, crossed out that letter N, and famously wrote VAR in red ink. But I'm most interested in that exclamation point, which is a unique notation to be found in scientific data. And if this is to mark the beginning of modern cosmology, that exclamation point is not self-explanatory, right? That there is some meaning latent there. So I wanted to follow that path that led to that exclamation point. And why that exclamation point exists is entirely because of this woman, Henrietta Leavitt, who worked at the Harvard College Observatory at the turn of the 20th century. And I myself found out about Leavitt's story, as Sian mentioned, when I was invited to the Harvard Radcliffe Institute. I was invited to develop a research-based exhibition. And because of my interest in astronomy shared with Jennifer Roberts, who invited me to the Radcliffe, we toured the glass plate collection. And I'll just give a little nod to Lisa and Tom here, who have traveled with me from the Harvard Plate Stacks. They're curator and archivist of this extraordinary collection. And it is the oldest and largest collection of astronomical glass plate photographs in the world. In fact, it houses, I believe, 25% of all of the glass plates, astronomical glass plate photographs in the world. So this extraordinary archive was opened up to us. And I took this photograph on the very first day, standing in those plate stacks. I have had many, many, many return trips there, generously supported by Tom and Lisa and others. An origin story for my own sort of special interest in that sense of finding our place in the cosmos, as it were, as to find a sense of home. I wanted to tell this woman's story far and wide. And so I developed my project centered around Leavitt at the Radcliffe Institute. But then, as Sean said, I was telling this story where, I'm in one of those careers where when you present something, you always get the question, what's next? And I sort of found myself sort of continually looking over my shoulder, looking back at Leavitt, and then just realized, oh no, I just want to turn around and go back to her because that's what's next. I want to stay with the story and tell it as deeply and as widely as I can. So this newly released book by the MIT Press holds some of the stories I'll tell tonight, among others. And let's sort of look at one of the stories of how we arrived at that exclamation point on glass. So like Edwin Hubble, Henrietta Leavitt studied photographic negatives. These were planes of glass coated with a light-sensitive emulsion, placed in a telescope, exposed to starlight, and so that each star, once developed, registered as a tiny black speck. And like Edwin Hubble, Henrietta Leavitt measured these circles of light, trying to correspond them to their brightness in the sky, trying to see where that information, where that measuring might lead her. This technology was a new technology, dry plate photography, and it was much more stable than its predecessor, wet collodion photography. And it allowed for these longer exposures, even multiple hour exposures, so that starlight could accumulate on the glass and pull these dim stars into view. This new technology was eagerly and ardently embraced by this man, Edward Pickering, who's the director of the Harvard College Observatory at the time for a span of a solid 40 plus years. And Solon Bailey here, this quote from him saying that in the condition of the science, there really was no foundation of knowledge to build any discovery from. And so Pickering really truly dedicated to advancing the field of astronomy, dedicated himself to this new technology, and quite ridiculously so. I mean, I don't know how many tons of glass, these guys know how many tons of glass are in the collection, but just the fact that by 1912, there's 200,000 glass plates in the collection, there's just this influx of data. And of course, to process that data, he needed a workforce. He needed someone, a labor force to process this data into sort of more manageable amounts. And so he was both progressive and practical. He opened up this rare access point for women in the sciences and hired women for this task. He was also practical. Despite being at Harvard, they did not receive university funding, so he had to be quite frugal and inventive in his funding, which he truly was. So as a result of this hiring of women, it became known as women's work to reduce the glass plates, and that was what their task was called. They were hired as computers, and I love that word reducing, because they're literally translating stars to using a mathematical formula to translate stars to standard coordinates, but they're trying to reduce the amount of information held on those plates for a manageable amount so that they build that foundation of knowledge to advance the field of astronomy. And I will say, this is the chapter opener in my book titled Women's Work, and this chapter goes into the history of women's labor in the sciences, but it was also called Women's Work quite literally, those two words applied, because they thought there was a sort of proclivity of women where they were trained in that early age in the art of embroidery, and that sort of exactitude of the hand and eye well matched this work. Now I'm pulling this paragraph from that essay in the book, and I'll read it here just to give you a context for where the field of astronomy was. 19th century astronomy in the United States was dominated by wealthy gentlemen scientists, that is the actual term, gentlemen scientists, and focused on the positions and motions of celestial objects. Astrophotography held new promise. Advances in dry plate photography technology during the 1870s enabled longer exposures, and this accumulation of starlight revealed previously invisible stars. The 7 stars of the Pleiades constellation, for instance, were transformed by a 3-hour exposure into a cluster of more than 1,400 stars. With this new depth of field, interest in the size and structure of the universe deepened. No longer dependent on the subjective impression of individual observations, astrophotography could make a record of this expanded space for deliberate, repeated study. The photographic plate became a site of shared knowledge. And so this true transformation, this technology transformed the field of astronomy, and the physical site of that shared knowledge was this building, the so-called brick building, where not only was the glass plate collection housed in this fireproof structure, but it was also where the women worked. And in Leavitt's time, exclusively women worked in this building. So I like to think of this idea of a room of one's own as a space for creativity. And here, these women had a building of their own. And a bit of subversion took place with this action, because you can see the observatory dome, one of the many observatory domes on the Harvard campus, behind that building. And that is where the men worked at night, making photographic plates of the night sky. And women were not allowed to operate the telescopes. It was thought that their disposition was too fragile. So they worked by daylight analyzing the glass plates. But because of this sort of outdated sort of thought that access to the telescope was a site of privilege, it was actually access to the plates that was where the action was. And so the women not only built this foundation of knowledge that future discovery could be made from, but they went ahead and made discoveries in their own right. And here are 2 extraordinary women standing on the steps of the brick building, Henrietta Leavitt on the right, and then I won't fully go, it's a whole nother book to go into Annie Jump Cannon's story, but she analyzed a different line of research, these spectra plates that captured stellar spectra on the plates. And this was actually the very first plate that she took observations from. And a macro photograph by Jennifer Roberts using her macro lens sort of conveys the complexity of this task that she developed from these glass plates, a classification system that is still in use today and is the foundation of our understanding of stellar evolution. But Leavitt's lane of research was magnitude work. So measuring those little circles of stars as they appeared on the glass. And at this point in time, right, we have to sort of come back to, even though this is, just at the again, so late 1890s, she's studying glass plates into the new century. At that time, there is no structure to the skies, right? So there seems to be a fairly even distribution of stars, and we don't know those pinpoints of light. Well, one that shines brighter, is that because that object is intrinsically brighter, or is it simply closer to us and therefore shines brighter? There is no way to know. And so that sort of, what is present is the size of the speck on the plate. And so that act of faith of measuring that speck and seeing where that research would lead her. And one of the places that led her was into this research with variable stars. So some of these tiny specks of light changed in size over time across plates. And here, as a lettered sequence by Leavitt, and those familiar VAR letters surface, she's identified a new variable star. She first looks for, finds that in these nebulous regions, such as the Orion Nebula, there's a particular density of stars, but also sort of treasure trove of variable stars, this beautiful plate taken in 1893. But when Harvard establishes an observatory in Arequipa, Peru in 1891, and places there the most powerful telescope in the world at the time, these 2 nebulous regions in the southern hemisphere are able to be captured and studied. So the small Magellanic Cloud and the large Magellanic Cloud, not yet known to be satellite galaxies outside our own, just simply fuzzy, cloudy regions, come into particular focus. And I include this page. All these cyanotypes are taken from a photo album that was assembled, I believe, by Solon Bailey, judged on the handwriting, and it's in the Harvard University archives. But I love that included in this, the most powerful telescope in the world at the time, this great ambition to establish an observatory to capture the stars in the southern hemisphere, and also the nicknames for the mule that carries the plates from the observatory to town. that then get transported 5,000 miles to Cambridge to be studied at Leavitt's desk. So I love this sort of familial quality to this as sort of scrapbook, as well as its scientific sort of advances. And so here's one of Leavitt's astronomical logbooks, and you can see that her attention really steers towards this new wealth of stars gathered. And one of the methodologies that Leavitt develops is inverting one of the negatives into a positive of the Small Magellanic Cloud. And then she superposes that over a negative of the same region of the sky, but taken on a different night. So with this superposition of a positive and a negative, those black specks, right, will fill in the stars on the positive. But a variable star might announce itself as a tiny misalignment of light. And just with that little indication, a suspicion, I should say, that it might be a variable, she digs into the work. And so here's another plate with markings from Leavitt. In this lettered sequence, she's circled at its center a suspected variable, and you can see its scale. And then around it, she has a lettered sequence that ascends the magnitude scale. So these are stars that they're more certain of their magnitude, and keeping in mind that, right, it's a logarithmic scale. So every new integer is 2.5 times less bright as you ascend the scale. So she's toggling her eye between that speck and another speck, trying to find a match. And that action just defines one data point, one estimation of its magnitude. But then she has to trace it across plates, across time, to find its pattern of wavering light. Now, I'm just going to throw sort of this litany of factors that Leavitt had to accommodate, just because I think sometimes when you think, okay, well, she's measuring black specks. I mean, yes, they're very tiny and subtle, but how hard can that be? Well, she's needing to figure out how starlight translates onto that surface of glass. So here she has a chart according to how much the registration diverges from the center of a plate to its edges based on different telescopes. And then there's just straight up defects on the glass plates. There's also this incredible challenge that the action of starlight on the photographic plate is not linear. So by the time you take a longer exposure to pull faint stars into view, those bright stars are no longer readable as a known magnitude, right? They've just become completely overexposed. And I won't go deep dive in the book. I do a deep dive into sort of muddle my way through all of the strange photographic techniques that Leavitt throws at this problem of standardizing magnitude. But one, just these are spectacular images. Again, using Jennifer Roberts accompanying me to the plate stacks and using her macro lens. But what she would do is these multiple exposure plates, so the same star shown here in this image 4 times, and she would add wire screens, grating, punched tin, prisms that deflected certain percentages of light. She had all these various techniques to dampen the light of bright stars. And then she would measure what she called offshoot stars. So here she could measure the diffraction spikes on that wire from that wire grating and compare it to a standard exposure on that same plate and sort of bring it into agreement with a mid-range star, and then add, by knowing what percentage she had diffracted it by, she could add that back up and get a true magnitude for those bright stars. So these really wacky techniques, I muddled my way through them. At one point, she had a prism that diffracted 1/100th of its light, and on the logarithmic scale, right, that's 5 degrees of magnitude. So this way that she's even just having to engage with the photographic medium and figure out how to sort of wrangle that language into some knowability, much less corresponded to the sky, is just incredible. And then one of the favorite objects in the collection, these so-called fly spankers, which I believe Leavitt it gets credited as naming. They resemble a fly swatter, but they're too much, as it said, too small to do a fly much damage. So they are fly swatters. But these, the women use these devices to calibrate between plates, right? So if you're having, let's say, different exposure times or taken by different telescopes, so how one star registers on the plate does not stay consistent across plates. So they would use the fly spanker to calibrate between plates, saying, okay, well, if it registers here on this plate as a 3 and here on this plate as a 5, I'll know that I need to add that calibration and correspond the 2 plates. Okay, so I just went through that slew of sort of methodologies and sort of photographic specificity just to arrive at this remarkable number of 1,777 variables that Leavitt herself discovered in Magellanic Clouds. Now, when she began this research, there were maybe only a handful, 100 known variable stars at that time. And so here she is discovering 1,777 of them. She goes on to discover 2,400 in her lifetime, which is more than half of all known variable stars at that time. So she is truly, again, that one access point into the sciences. The women are there in the brick building, and there they are pushing the frontier of knowledge forward. So this very important sentence is included in Leavitt's paper, published under her own name in 1908, saying that it's worthy of notice that the brighter variables have the longer periods. So what she's associating, right, is that she's tracing across time these stars going dim to bright and dim again, completing a pulsation period. And she notices that it seems that apparently the larger they are, the longer it takes for them to go through that pulsation period. Now, she decides to pursue this line of thought, and she assumes, again, nothing about the structure of the heavens is known. And so she makes this important simplifying assumption that, okay, I'm going to treat all stars I find in the small Magellanic Cloud as roughly equidistant. If a star in that cloud there's a bright and a dimmer star, they travel the same distance to touch that glass surface. Therefore, they've been dimmed equally by that distance. So when they land on her plate, the relationship there between bright and dimmer holds true as that in the sky. So this is the very first time that a relationship in the heavens has been brought into contact with a physical object on Earth. And so with this assumption, she goes and tries to establish these light curves for her variable stars. And I'm using this historic photograph, a posed photograph of the Harvard computers, because I was fascinated by this photo for a long time. It took me a while to recognize that there's a light curve just to the left of Antonia Maury's shoulder there holding the magnifying glass, that there's a light curve for Beta Aurigae dated December 1889. So you can see, hopefully, yes, quite well, that there's these data points, right? And so they're establishing these data points through time and then connecting that into a light curve. Well, I like to point out in the pages of Leavitt's logbooks that here she is tracking two variable stars, number 10 and number 13. And then in this little sketch I love, I found another one, new variable, number 86. She adds that to the list. But as she's pulling these data points, I want to point out that one of the plates she's studying is from 1904. The second one is from 1896. So as she's pulling these data points, trying to accumulate an understanding, right, she needs to sort of pull one and hold it and then go to a random place and pull it again. She's not watching that star, right, fluctuate in the sky over time. She's really needing to build these light curves and so that emphasizing that in this sea of data that she's able to sort of pull forward any kind of understanding whatsoever is extraordinary. But she does it, and in 1912, she announces the period. She's established the light curves for 25 of these variable stars. And with this published paper, she publishes this extraordinary graph that there is a direct relationship between the amount of days, the number of days a variable star takes to pulse, and its apparent magnitude. So because of the smoothness of this curve, which is first known as the period luminosity relation, because of the smoothness of this curve, it could be considered law. And in fact, today is known as the Leavitt law. Astronomers immediately recognized the potential of this finding. They knew if they could go and calibrate a handful of the nearest Cepheid variable stars that she studied in the cloud, if they could use a bit of trigonometry, the parallax, and calculate the physical distance to those stars, they could tie her relationship to physical distance. They could go back to the cloud, use Leavitt's relationship, and know how bright those variable stars should be. And then using the inverse square law, they could use a very simple formula to calculate how much that light is causing that star to be dimmed. And so Einar Hertzsprung is the first to try to calibrate Leavitt's law, and he comes up with this figure that the small Magellanic Cloud is 30,000 light years away. And famously, at least in my mind, a zero is dropped when his findings are published, and sort of jaws drop that, oh my God, the small Magellanic Cloud is 3,000 light years away. This is a staggering number. Little did they know it was actually 10 times that. So the very first application of Leavitt's law has already expanded our known expanse of space. And I, again, like to point out that it often is said, oh yes, well, Leavitt established this law, but did she know its ramifications? And I just am like, well, yes, it's right there in her paper. It is to be hoped that the parallaxes of some variables of this type may be measured. So she's very aware of how this law can be put to use. And so we have this physical distance to the Small Magellanic Cloud. Well, now it's the question of, well, can this law be applied elsewhere in the universe? So this law of this pattern of light that she's noticing in these stars, this sort of quick rise to brightness and then this slow decline, and a quick rise to brightness and a slow decline, very much in my mind, at least, like a heartbeat. Well, does this heartbeat hold true for other variable stars in the sky? And this contact print that I'm using as just as a demonstration of the cloud actually has this little, it's a contact print made from one of the glass plates. And here it's written sequence 35, Miss Leavitt's region, which I, of course, rather like. But this contact plate also holds these two strange celestial objects, these globular clusters that also contain variable stars. And so globular clusters are these relics of the early universe. There's these conglomerations of tens of thousands, sometimes hundreds of thousands of stars, densely packed. And I love how they sort of seem to pool on the surface of the glass, and here it sort of bore into the paper. But Leavitt is noticing this as well, is that there's this familiar pattern of light that she's recognized in the cloud, also present in variables in globular clusters. However, some of those cluster variables they're sort of much more blinking lights. That they complete that pulsation cycle in under 24 hours. Where her variables in the cloud have much longer expanses, all the way up to one she charted at 128 days. But Harlow Shapley, who's at Mount Wilson Observatory at this time, not yet, he is the director following Pickering at the Harvard College Observatory, but as a young astronomer, he's at Mount Wilson, and he has the same question. He's studying globular clusters intensely, finding some of these Cepheid variable stars that he knows holds Leavitt's law, but he's wondering, the cluster variables that he's also finding there, do they hold? Does the same law apply? And he's writing Pickering. These are in Pickering's files of, does Miss Leavitt know if these variables she's finding in the cloud, well, do they have shorter periods? That is, are they shorter than 1 day, similar to cluster variables? And then just a month later, he's like, hey, still wondering. And he's writing this declaration, her discovery of the relation of period to brightness is destined to be one of the most significant results of stellar astronomy. So true, it's founding, in fact, modern cosmology. So Shapley goes ahead with this assumption. Let's say that Leavitt's law applies to these cluster variables. Oh yes, and then again, just providing evidence that Leavitt is part of the conversation. There it is in her paper saying she's too wondering, well, I have this law. I'm wondering if I can further study the cluster variables types. Are there limits to their mass? What are their spectra? So she's like, how can we further investigate this issue? But again, Shapley decides to pursue this research, and he does this very elegant application of the Leavitt law. So remember, we're swimming in a sea of stars at this point, right? So the stars are fairly evenly distributed across the sky. We have no sense of structure to them. There's not this realization yet that most of the stars are sort of hidden in galactic dusk in the disk. But these globular clusters, these young, sort of formed in the early universe, they've migrated right from the galactic disk. So they're more in the halo of, or so they're sort of more suspended throughout space. And so he thinks, well, if I can apply Leavitt's law to these strange objects, maybe there's an underlying structure that surfaces. And that's exactly what happens. He applies her law with extending the cosmic ladder out to 119 globular clusters. And he finds that 30% of them, this sort of what he calls a cluster of clusters, assembles here. And then this enormous expanse of space is drawn out. And guess what? Our sun is far at its edges. And so he's provided this skeleton of the Milky Way, and he realizes the sun is far outside its center. We now know that there's a supermassive black hole at the center of that cluster of clusters. But this total reorienting, our new worldview, right, is almost as dramatic as the Earth is not the center of the universe, and now the sun is not the center of the universe, right? I'm not even using the word galaxy yet because there are no galaxies. There is just the sea of stars that we swim in. So this structure of the Milky Way is established. And so when a discussion turns to, well, what are these spiral nebulae in the sky? Shapley says, I don't care what they, I don't care what they are, but I'm sure they're within these enormous confines of the galaxy that I've just established. So that is why it is so profound when Edwin Hubble finds one of those Cepheid variable stars in Andromeda Nebula. he knows immediately that he can calculate the amount of distance to that star and prove that Andromeda is so far away, it has to be a galaxy in its own right. There is that exclamation point. And then when Hubble goes on, each time a Cepheid is identified in a galaxy, or in a nebula, it becomes a galaxy. And in 1929, this famous paper that shows that not only are there galaxies all around us, but the farther away they are, the deeper redshift in their light, the faster they are accelerating away from us. And so this expanding universe, the revelation of our expanding universe opens up yet another sort of reorientation of our worldview. And I like to point out, one, just to like sort of Hubble certainly is a household name. If you know any astronomers, it might be Galileo and Edwin Hubble as the sort of the two top choices. But I like to point out that it was actually a Catholic priest and mathematician, Georges Lemaitre, who solved Einstein's field equations for an expanding universe, but then paired it with observations. So he actually visited Edwin Hubble in 1925, was deeply following this cataloging of galaxies and their redshift and light. And so his 1927 paper, it not only mathematically proves an expanding universe, but also in the title you can see that it accounts for the increasing radius, accounting for the radial velocity of extragalactic nebulae. He's still tagging on that nebulae. They're not yet. They're galactic nebulae. So here, just recognizing that science is a collaboration and an ongoing conversation, and that Georges Lemaitre is actually the first to pair theory and observation together. Einstein famously resisted the solution to his own field equations. He had added a cosmological constant to keep our galaxy, our universe at this time, static. So that's how much this was a new worldview, that going from galaxies existing beyond our own to an expanding universe is just a complete reorientation of where we are. So in tribute to this long scientific narrative and to Leavitt's contribution, this foundation of that, I wanted to make an art object, which is what I do, honoring her life and work. And so I made two quilts. One shows the stars above the place of her birth on the day of her birth. And the second panel shows the stars coming back into view on the day of her death above the place of her death. And I developed my own magnitude system to translate starlight into thread. And so I used star calculation software. It sort of mapped out the stars 2 hours before dawn on the day of her birth and gave them my own magnitude scale. And then one by one, I played time forward and traced that trajectory with chalk until, depending on its brightness, it burned out with the rising sun. I then again, adding corresponding my magnitude to the grayscale, I then translated this pattern into thread. And here are the stars coming back into view as the sun sets on the evening of her death. In terms of labor embedded in a piece, this is very true of here, where these star trails, again, I wanted this idea of this fading light and returning light. And so each couple of inches, I would change the thread color into the grayscale, and so it disappeared into the depth of the black fabric. Now, this quilt diptych anchors my exhibition at the Radcliffe, and wherever it travels, this quilt is shown. But of course, not only is this work a monument to the reverberations of her discovery, but held there is her lived life. And I wanted to examine that aspect of her work just as closely, because part of this story is that this light curve that Edwin Hubble produced to accompany his glass plate, this is right. That plate was taken just 2 years after Leavitt's death. And so here you can see those data points that Hubble's tracking. Once he suspects that variable, he does Leavitt's same task of following that path light. But here I'll point out he can play time forward. He can watch that one star. And I'll notice in his light curve, right, it says successive days, February 5, 6, 7. So here he is tracking that light day by day by day, not a luxury, I will point out, that Leavitt had. And so yes, Leavitt missed this revelation just by 2 years, her life cut short by cancer. And so it made me sort of, in some ways, despair. Well, if you don't arrive at the destination is the path there worth living? Let's really get deep into that existential question, but that is the question at hand. And so turning to her life lived, what do you find there? Well, you find these marvelous objects, the glass plate. And here is a lettered sequence. It's not even a Cepheid variable, despite being in the constellation Cepheus. It's a mirror variable that has a period of 388 days. But I love how Jennifer's photography, right, captures some of that magic held on those plates, some of that fascination that Leavitt so obviously committed and held. And this is perhaps my favorite photograph of Jennifer's, where that outlying star labeled B with that ink nib hitting her side of the glass, Leavitt's side of the glass, sort of reaching for that emulsion star, and that effort of trying to bridge these two worlds. And in the pages of her logbook, the care and dedication that Leavitt takes, again, these beautiful framings by Jennifer's photograph, but even the precision of her cursive, I feel, embodies who this woman was and what she cared about. And this delicate image that reminds me of an Emily Dickinson poem. Again, these sort of staying at attention and right on the edge of certainty and doubt, and just walking that line. Also held there is this group of women that work together. And an extraordinary fact about these women is that almost without exception, none of these women married and none of them had children. And just pausing on that for women, white women of this social class to make that choice, it is an extremely outlying choice. I no doubt, and trying to read stories, there are individual choices for each one of those women, but collectively what I found is that they cared about the work, and from that caring for the work, cared about each other. This photograph as well is an important community of people, and I this is the gathering in 1910 of the American Astronomical Society, which includes European delegates. And what I like to show, if it's not, which I feel is self-evident, is how integrated these women were into the astronomical community. So that is one surprising aspect I found in my research, that you think Leavitt is not the household name that Leavitt is. And there is this assumption, well, the sexism of her time limited that visibility. And what I found is that Leavitt was extraordinarily visible in her time, and is actually our sexism placed on the telling of history that needs to be clarified and cleaned. And I like sometimes to toggle between these two photographs, that, right, sometimes there's this sense of like, oh, this collective, this group of women focusing on that warmth and collaboration between the women. And I like to say that I believe that the warmth of this community allowed them to excel, and that their excellence brought them back together too. So I think those two photographs are very much in conversation with each other. This sweet line by Leavitt's mother I also pull forward, written just a week after Leavitt died, writing to Shapley, who's the director of the observatory by then, and just saying, but while she was so modest about it, a remark once in a while showed me that she understood the standing she had among the astronomers. And I like that Leavitt did know. She knew that of her significance, that her work was seen, and that she derived enormous pleasure in that work. This is a page from Annie Jump-Cannon's scrapbooks. And one fact that I'll just call forward about these women is that both of the women pictured here, Annie Jump-Cannon and Henrietta Leavitt, were described in their lifetime as being deaf. For Leavitt, that appears to be a progressive loss of hearing in her 20s that resulted in a complete loss of hearing. For Annie Jump-Cannon, it was scarlet fever at Wellesley that impaired her hearing, but she was known to attend the opera with a hearing aid and to remove that hearing aid when concentrating in work. And I offer that fact just as a fact. Again, it's one of those facts that is part of this community. It's an extraordinary fact because that disability was not accommodated in society, much less in the workplace at that time. And in fact, there's written evidence of Annie Jump-Cannon being nominated for an astronomical prize and completely rejected simply based on the fact that she was described as being deaf. So there is an incredible bias there. But I also will note that when Solon Bailey writes Leavitt's obituary, it is not a fact that he mentions. He does not mention that she is deaf. and that is the term they used at the time. And so I think there's also this way, again, that there is a love of the work, and from that, they formed what I would call an observatory family, and we're family to each other. And then I like just to see the thinking of Leavitt's mother saying she knew the standing she had among the astronomers. So with Leavitt's presence asserted, I'll just end by just touching on the way the Leavitt law still remains relevant in contemporary cosmology. So here's that historic star, that one Cepheid variable that when the Hubble Space Telescope was launched, they actually did just a sort of an honorary salute to this profound star. And in this one chapter of the book, I speak about the relevancy of Leavitt's finding. And I worked with cosmologist Wendy Friedman, who was directed the key project of the Hubble Space Telescope. And the key project, its mission was to measure the expansion rate of the universe. So if you look back at Hubble's law, which is now being known as the Hubble-Lemaitre law, to give credit to that significant work, that law is the relationship between distance and radial velocity. Now, if the distance to galaxies is calibrated, if it's refined, right, and distances stretch out, the slope of that line is going to decrease. If the galaxy distance are measured to come in, it will increase. So this expansion rate of the universe is based on the angle of that slope. So the key project, the key scientific mission of the Hubble Space Telescope was to measure. What did they use? Well, they used Cepheids. So here's a sample of 800 Cepheid variables that they measured using the Hubble Space Telescope, and look at that complete agreement with the Leavitt law. So an interesting note is that in making these measurements, Wendy's number came in, the expansion rate came in at a number that was in disagreement, that there were actually stars in our universe that were older than this expansion rate would allow for. So, where do we sit with that? And what I love is Wendy's a true observational cosmologist. She says, well, sometimes when you measure something, it reveals something, and sometimes it reveals when you don't know something. And in a few years' time after this finding, dark energy was discovered. It was discovered that our universe is not only expanding, but accelerating. And those numbers came into agreement. So again, I love that sort of return to faithfully and truthfully seeing. And you have to sometimes be very inventive in ways that you see, but to see clearly and see where that leads you. And here when is an image Wendy shared with me from her time on JWST. And so look at this remarkable resolution, same star seen on the Hubble Space Telescope and now JWST. And this Cepheid is over 60 million light years away. And Wendy says it's blinking just as consistently and predictably as Leavitt said it would. So this investigation continues, but there's that same return to the action of measure a circle of light and see where that information leads you. So the final thing I'll end on is a drawing series I did based on this astronomical glass plate held in the Harvard Plate Stacks collection. And it was taken in 1934. So this is, Leavitt died in 1921. So this is in that decade of revelation that comes from the implementation of the Leavitt law. And in 1934, we can calculate the distance to these three objects in space. We know where they are in three-dimensional space. But in Leavitt's lifetime, it was just two-dimensional, a surface of glass. And so to honor that transition from 2 to 3 dimensions, I first made a drawing using a pencil of that photographic plate, which is shown here. And again, I sort of did that same picking up a pencil, which I normally pick up a needle and thread, but I picked up a pencil and was like, let's see if I can just hold my attention and follow the path that Leavitt followed. And so that was the first action I took, and I won't read these sections from the book, but what I noticed was at the edge of the plate that there was that particular distortion, and because this wider field of view on this plate was exaggerated. So I really started to hone in on these strange artifacts produced at the edge of the plate. And what I did was I magnified sections of the plate and just followed star by star these strange transfigured shapes. And in some ways, the distortion animates the stars. I mean, they really are sweeping towards the edge of the plate, almost about to take flight. But it also is a reminder of the lens through which we see, that sometimes when we use technology, we think there's a certainty to the technology, or we even forget the lens itself. And so that reminder that we are always looking through a lens and we always need to be aware of perspective as we see is central to this work. Here is a framed view of from a distance, but for the book, I didn't want this sort of distance approach. I wanted this close looking, and that's where Jennifer Roberts' macro photography animates these strange stars. And so I'll run through some of the images that she collected, this sort of taxonomy of starlight, these strange shapes, again, all collected on the same surface of glass. It's almost like each corner is its own ecosystem. But in that sort of attentiveness to each individual star, I returned to Leavitt's process that looking for, but she held faith in that action of measuring a star and seeing where that would lead. So I'll end there. Thank you. Thank you. I don't know if we all want to stretch our legs, but I'm open to questions as if there are any, or can have individual conversations as well.
Right.
Yeah.
Well, should we open it up to the floor? We have a microphone because we have quite a few people listening and on Zoom. So if you have a question, it would be great if you could share that with us so we can have that conversation. Any questions?
I know it's daunting to hold a microphone.
Stand away.
Yes. Okay.
So I'm really interested to hear you talk about John Cannon and her relationship with Leavitt, and how you alluded to the fact that Cannon's whole life work and contribution is another project in its own right. Is that next, or would you like to share a bit more about Cannon's work with us?
Yeah. So I know it is extraordinary. So Leavitt, in terms of the three-dimensional cosmos, it really isn't an exaggeration. Hopefully I've made my case here that her discovery founded modern cosmology. And Annie Jumpkanon's work is equally significant in founding our understanding of stellar evolution. And so she categorized, I believe, like 358,000 is the number that you guys would know, but I believe that's the number of stars she classified their spectra. And because she made such a consistent classification that was just spot on, that is the beginning of this understanding of this correspondence between luminosity and temperature, again, revealing the fact that stars evolve. So truly, the foundation of knowledge is entirely Cannon and others, of course, that other women that worked at the Harvard College Observatory supporting that work. But yeah, she was an extraordinary woman. And I mean, I'm tempted by that because I am that what next question is present. I will not say that it's not. It is an open possibility, I would say, because it's just fascinating, these stories, how significant they are. One of my favorite stories about Cannon is that when Shapley came to be director at the observatory on his first day, he's like, oh my, the famous, I mean, she was, it's like he called her the famous and jolly Annie Jumpkanon. And he said, oh, I've had this variable star I've been wondering about. And he said the star's name. And she calls to her assistant. And I like to point out that she had assistants. She calls her assistant and says, oh, will you get plate number da-da-da? Brings that plate forward. And Shapley says, and that star was on that plate. So that was the sort of comprehension that she held, which is just astonishing. Yeah.
It was really kind of nodded at the Royal Astronomical Society. I do have to say that she was nominated for the gold medal like 9 times.
Yeah.
Never actually awarded it, which is a shame. But she was given recognition in other ways. She actually, I believe she gave a paper to this very room. That's it.
Cool. Oh, that's very cool.
Hi, thanks. Great talk. I think that's great dedication to her life. Fascinating how you what I offer. Do you feel like you've grown close to her, or like maybe softly and this whole element of stars and mapping it out and having this art? Do you feel like she's quite close to you now? And obviously, when you first discovered her and then go through this whole journey, this summer. How do you feel? Do you feel like she's quite close to your life now?
Yeah, absolutely. Yeah.
It's fascinating how you mapped it out and going about work and research and brought her life in this form. So how do you feel? She just personal level?
Yeah, no, I appreciate the question. It is interesting. I thought of that in the way that I pulled her close to me, and I thought, oh, well, what would she think of me? And I hope I've done her justice, certainly. But one thing I do appreciate about Leavitt is that, as evident, the art objects I make are very labor intensive, and there is that sense sometimes where it's like you finish a piece and it's like, phew, okay, there is the thing that I made. And in following Leavitt's path, I found my own investigation of, oh, wait a minute, it's not the object itself. Of course, you want that object to be something and to live out in the world in some way. But again, if the path there is not an engaged one, it is not a worthy path. So that is truly the gift I feel that Leavitt has given me, to engage in the very present that we are in.
I love the title of the book.
Thank you.
And I wondered if you could discuss the ways it's about the one of the things, two-dimensionality and three-dimensionality. If there's a coming that made it.
Okay. These are two big questions. One, I like that this is my friend Jen Bourbon in the background. So you alluding to the Radcliffe Wave, is that what you were alluding to inside? Okay, I like that. She's giving me a leading question. But there's so many facets to this book, but there are 3 guest essays in it. And one of them is by astrophysicist João Alves, who was a Radcliffe Fellow when I was there at Radcliffe. And during that year, he discovered the largest known coherent structure in the Milky Way. And I got to see that evolution of discovery and be in conversation with João. And it's somewhat a famous story now because when the Radcliffe wave literally rides the galactic plane above and below the plane. And when I first met him, it was what a so-called ramp that was underneath the galactic plane. And he credits, I do not credit, Jen has forced me to say it, but seeing my exhibition and seeing this hand stitch ride the galactic plane, that he is saying, okay, this is a 10,000 light years, expansive structure. Where do you look next? And that faith in the stitch, and sort of he looked above the plane and then made that link of the ramp into a stitch. So there was this real beautiful evolution of how art and science are truly in dialogue. So thank you, Jen, for making me tell that story. And then thinking about where my work goes from here. Well, Sean alluded to it, but I got an artist research fellowship at the Smithsonian and studied dark matter as a structuring force in the universe. And so I'm very much interested in those forces at play. So to me, I'm actually not at all interested in particle physics. Sorry for any particle physicists in the room, but I'm interested in sort of dynamics and forces. And so one thing I love about dark matter is that we don't know what it is, but we can see what it does. And so, yes, I'm going to go back to the studio and play with string and think about dark matter.
I have a couple of questions from online. From YouTube, I have Anne Cat, who's watching me from Nottingham today. They ask, does extinction affect the period-luminosity relationship? And they were also intrigued by Andy Jenkins, another great scientist in that team, which you've spoken about. And we talked about that. And they say that they're interested to know her story as well.
Yeah. So I'll just, well, and that's, so extinction, dust, I assume they meant dust extinction. It very much affects. And so thinking back to these photographic plates where red stars barely registered, of course, interference from dust absolutely affected how these stars registered onto glass. So that's something I like to emphasize, is that when something is discovered, it sort of is pulled up right out of and seems so self-evident once it appears, but recognizing the complexity that Leavitt had to navigate. And it's fun, even talking to Wendy Friedman, she talks about literally mapping, reading these stars, these Cepheid stars in different wavelengths and seeing how dust affects the readings. And so on the Hubble Space Telescope, which again, I dive into in the book a little bit more, but they're able to calibrate, they're able to account for dust. And then guess what? James Webb sees through dust. So there's this new relationship with Cepheids and their clarity.
We might have found about actually too around studying, also if you have a circuit, you can use the machine, and also wonders if you connect your tech cell with the stars with the Jumper connection to computers.
Oh yeah. So right. So a couple, I always like blitz over that. Like, yes, I do all of my sewing by hand, and partly thinking back to this Radcliffe wave, right? So if you think about a single thread strand rising above and below a surface, so it dips down and makes a stitch underneath and then comes to the top. And what you get with hand stitching is this dotted line, where if you think of machine stitching as two interlocking threads that make a solid line. So one of my allegiances is not just tying back this data in a relationship to the body, which is certainly central, but I also love that dotted line. And so that what I call the uncertainty of the stitch, we're translating this data into a sort of a liveliness is important. So I use that hand stitching. And then I am not at all a jacquard weaver, but there is this direct, right, in this sort of early days of computing, there's this direct relationship between weaving and computers and different form of computing. But I do like thinking it is a nice evidence of how, what appear as separate disciplines are very much linked and very much share a framework.
Thank you. My question is about the pieces themselves. Approximately how long would it take you to make these pieces when you're stitched instead of?
I know it takes an extraordinary amount of time, and I like to say that I like don't ever like to calculate it because I was in this like little television program, and they were in the different question, but how many stitches are in a single quilt? And I was like, oh, please, I do not want to know. And then they went and did a square inch, calculated how many, and it was like in the hundreds of thousands. And I was like, oh my God, you've cursed me to like start a new piece and just be like, there's 4. And then, and so part of it is like, that's partly why Leavitt's story is so meaningful to me, is that reframing that commitment of time is that I very much believe that time, and I did not read excerpts from the book, but I speak about that, how I place time in the objects, and I believe they hold them there. And truly looking at these glass plates, which these two individuals have helped preserve through time, I very much felt Leavitt's presence held there, presented back to me.
I was wondering what was the attitude then in Australia? Because as I understand it, was already.
Yeah, no, right. And right, were very intertwined in their history. And here I would say it was fully separate in that, they're really going back to Pickering and Leavitt really sharing this sense of, well, how do we advance the field of astronomy, and thinking like that speck is the piece of information they had to build their understanding from. So it was really committed to measuring in repeated actions and then following that line of work. Okay.
Okay, we've come up to 7 o'clock now, so no other questions. I'd just like to personally thank Anna for using the lens of her, not just her artistic work, but your words, your texts, to interrogate art and science and history in a fantastic talk. So let's thank her.
Thank you. Thank you so much. Oh no, I'm remembering that. 3 bucks in habit, but 4 I wanted to get. Okay. Oh, 5.